Here we are for Module 7 on nuclear issues. In this module, we're going to look at a couple different things. We're going to look at nuclear accidents, like from nuclear power plants, and we're also going to look at nuclear weapons and their potential for devastation and destruction and apocalypse. And so, oops, there we go. I'm going to talk a little bit about types of radiation and a little on nuclear plants and how they work and different power plant accidents. And then after that, we'll talk about how nuclear bombs work and talk a little bit about nuclear tests and your catastrophes. There are a couple other videos that go along with this module besides this video lecture. So I'll try to keep it fairly brief in this video lecture, but we will talk a little, because there's more information that will come through the discussions and the other videos. All right, but first, a couple of things just to foreground, because there's not really too much in the other videos. One of the first videos that you should take a look at is the difference between fission and fusion reactions. Nuclear power plants and older nuclear bombs were fission, are fueled by fission reactions. And then hydrogen bombs, the larger nuclear weapons, are fusion reactions. We don't currently use fusion for power generation, mostly because the technology just hasn't advanced to the point where we've been able to actually get more energy out of a controlled fusion reaction than we can put into making one happen. And so because of that, fusion isn't used for power generation. If it ever comes to the point where we are able to get more energy out than we put into those kind of reactions, it would be a real revolution in terms of energy production, but that's not something that has happened yet. All right, so, and if it might even make sense to pause this video if you haven't watched that other one on fission and fusion. You should kind of watch that first so you have a basic understanding of how the nuclear reactions work. So, one of the things is that when we're talking about these kind of nuclear reactions, a lot of these nuclear reactions are done with either uranium or plutonium. And uranium is something that is a natural element that exists, that can be mined from the earth. And plutonium is an artificial element, something that has been created by people through the use of other kinds of nuclear reactions. Now, the thing when we talk about like radioactive contamination, sometimes we're talking about uranium and plutonium, but we're also talking about other byproducts that come from nuclear reactions that can be quite toxic when they're in the environment. And so just to mention first here that uranium has a couple of different what are called isotopes. And for those of you who've had some chemistry or background in chemistry, can understand that concept, but basically there are different types of uranium. Almost all the uranium out there is what's called uranium-238. This is something that can't really be used for fission reactions. About 0.7% of all uranium is what's called fissionable uranium, and it's called uranium-235. And you can see the half-lives here, 4.5 billion years for uranium-238. And a half-life of about 700 million years. And what a half-life means is that the way radioactive decay occurs is that the atoms in these substances will break down at a very predictable rate, but it's not a linear rate. It's something that changes. It's a logarithmic rate or an inverse logarithmic rate. And basically what that means is this. If you have a pound of uranium, let's say you've got uranium-235, if you have a pound of that, in 700 million years you'll have half a pound. In another 700 million years, you'll have a quarter of a pound. In another 700 million years, you'll have an eighth of a pound. So it kind of keeps dissipating, but not totally disappearing through time. And so different radioactive elements have different half-lives. And with uranium and also plutonium, these are very, very long half-lives. But a lot of things that are actually dangerous right after nuclear disasters or nuclear weapon detonations actually have half-lives that are much shorter than that. Like for instance, iodine-131 is a major contaminant after a nuclear disaster. It has a half-life of 8 days, meaning that after 32 days, right, you actually have lost a tremendous amount of this that doesn't exist anymore in the environment. It's really kind of reacted and is no longer around. But iodine is a very big problem if you're exposed to it right after an accident. Like for instance, near nuclear plants in the United States, people will keep iodine pills on hand because one of the things you can do is flood your body with regular iodine so that if there's a nuclear accident, radioactive iodine doesn't flood your system and create thyroid cancers and things like that. That's a problem in places like Chernobyl and Fukushima and other areas. Even around Keene, when the Vermont Yankee plant was in operation, the schools and things around the nuclear plant would have uranium pill or iodine pills on hand. So one of the things about uranium is that because such a small portion of the uranium you find is actually fissionable material, this means that it's very difficult to kind of separate out that fissionable material. So when you hear about like countries like Iran or North Korea, when they were having problems coming up with weapons, nuclear weapons, the problem was not finding uranium. The problem is refining the uranium and taking out the 0.7% that's actually fissionable. You may sometimes hear the term centrifuges. That's a way of sort of separating out the fissionable uranium from the massive uranium, which doesn't really work as a weapon or as a power generating source. And so that's one of the big challenges if you're trying to get uranium that you can use is kind of sorting out the fissionable from the unfissionable. All right, so one of the things that I also want to mention while I've got this slide up here are two things here, cesium-137 and strontium-90. These are other major contaminants that you get from nuclear weapons detonations and also from nuclear plant disasters. So for instance, in places like Chernobyl and in Fukushima, the major problem is cesium in the landscape because that's the major contaminant. And where that comes from is after uranium or plutonium splits and starts to break down, these are some of the particles that are left over from that. And these have half-lives of about 26 to 28 years. And so because of that, it means that if you get this stuff in the environment, it takes many, many decades for it to really kind of dissipate in the environment. Okay, so that's kind of a discussion of what uranium and different kind of isotopes, but these different isotopes that are radioactive also have different kinds of radiation, and it's important to kind of recognize this because when we talk about radiation in the environment from nuclear disasters or from nuclear bombs, there's actually a few fairly major differences in the types of radiation. And the main ones that I want to talk about here are alpha, beta, and gamma radiation. Alpha radiation is a type of radiation that actually can be stopped fairly easily. A piece of paper will stop alpha particles. However, alpha particles are relatively big, and so if you inhale these or ingest them into your body, yes, they can be stopped by fairly thin tissues, but they have so much energy it can create a lot of damage inside of bodies. Yes, your skin can stop it and all of that, or even pieces of paper or even just clothing. But if you get it in you, it's really dangerous. And so uranium and plutonium are examples of alpha emitters. That's the kind of radiation they put out. Beta is another kind of radiation, and it's a little more penetrating. It will go through and into your skin. It will cause burns. It will go through paper or clothing, that kind of stuff, and has a little more penetrating ability. Then we see what like medical x-rays are like. They can penetrate through obviously your flesh but not your bones. That's how you can see things on medical x-rays. They can go through wood but not really through cement. Gamma radiation is another kind of radiation produced by nuclear contaminants and also from nuclear weapons and stuff going on. And these are very high energy, very high penetrating forms of radiation. Gamma will go through a piece of paper, it'll go through your whole body, it'll go through a bunch of wood, it'll even go through almost 6 feet of concrete or cement. And so gamma radiation is very penetrating, but it's not as the particles are actually very, very small to the point where they talk about it more as a wave, almost like light. And so even though it penetrates a lot, it's not quite as damaging as alpha particles. But if it's in your environment, there's very little you can do about it. It's just penetrating your body from every which way. And so it's kind of important to recognize that there's different kinds of radiation when we talk about radiation in the environment. And we'll get back to this when I talk about Fukushima here a little bit. Okay, so keeping on the theme of nuclear reactors first, or kind of addressing that first, nuclear reactors are facilities that generate electricity by taking uranium and essentially putting uranium in close proximity to other bits of uranium, other what's called fuel rods, and getting these self-sustaining reactions where the uranium essentially will generate heat. And the way that happens is you get what's called a chain reaction, which is a uranium atom. If you saw the video on fission and fusion, right, this is a fission reaction. Uranium atom splits in half. Neutrons are kind of come out of that, which hit other atoms, which then break those apart, and those break other ones apart, and it kind of goes in this chain reaction, and it generates a lot of heat. And basically what happens is you just have this uranium or plutonium kind of reaction going on in here, and what it's doing is heating water. You're using that very hot water to basically heat another source of water and turning it into steam. And that hot water from the reactor is just sort of being circulated here. The heat from it is being moved over here to this water to create steam. You throw the steam through a turbine, which then spins a generator. And all a generator is essentially magnets with copper wire around it, and that's what creates electricity, is the spinning of that magnet through the copper wire. Now, this is how not all, but most electricity is generated. You can have a coal-fired plant or an oil-fired plant, and the only real difference is that you're heating the water with oil by burning oil or burning coal. In hydroelectric dams, you just have water running through a turbine that's falling like through a dam, and that's what's creating your electricity. And so nuclear plants, all that really is that uranium is used for is the heat source to heat up that water. So one of the things that happens, this is also just a more simplified version of this kind of nuclear reactor, but again, the reactions here, it's just really to create heat to boil the water and spin the turbine. Well, with nuclear reactors, sometimes things go wrong, and a couple of different examples of this are the Chernobyl disaster in the Ukraine that happened back in the 1980s. And they were actually doing an experiment, kind of like running some tests on the reactor that when this accident occurred. And in 4.5 seconds, the energy level of the reactor increased 2,000 times. The cooling water, all of it converted to steam and blew the 1,000-ton concrete roof off the whole reactor, and then the reactor caught fire. And one thing about nuclear reactors is that, or nuclear reactions, if I back up here a second, is that this nuclear reaction, to make uranium react, all you have to do is kind of put it in close proximity in a certain density. And so you have to then control the reaction by putting what are called control rods that kind of soak up the neutrons to kind of keep the reaction from going. But if you kind of walk away from that reaction, it will just go. You don't have to keep adding heat to it or anything like that. It will just have a chain reaction and generate its own energy, which is exactly what happened in Chernobyl. They lost control of the reaction. It just went out of hand and blew up the building. And from Chernobyl, there were 37 deaths. 500 people were hospitalized, many with acute radiation sickness, and over 100,000 people were evacuated. About a quarter of those had received fairly high doses of radiation, because when the reactor caught fire and it blew the building apart, all the radioactive particles went into the air and then settled over this large area of the Ukraine and Belarus. And one of the biggest problems was iodine-131, which I mentioned. It only has a half-life of about 8 days, but when you ingest it and stuff, it really does a lot of damage to your body, particularly your thyroids, and creates thyroid cancers, which then became very prevalent in that part of the world after this disaster. And this is just kind of what it looks like where it blew the building up here at Chernobyl. And there's a whole video here. I didn't necessarily assign this, but for those of you who are interested, it's very good. One of the things that really kind of this video shows about Chernobyl is that it could have actually been much, much worse than it was. There was after the accident, some of the nuclear material could have melted down, hit the water table, and created a much, much larger explosion, but luckily that did not happen. But that video kind of gets into some of that history there. Now, the more recent nuclear disaster from a nuclear plant is the Fukushima disaster. And in Fukushima, what happened is this reactor was just operating as normal, but there was a very large earthquake that ruptured this whole area of the Pacific offshore from Japan. Fukushima is this prefecture here. You can see where Tokyo is down here a little bit further south. And this large earthquake created a tsunami, which, we've talked about tsunamis, of course, in this class earlier. And that tsunami hit the nuclear plant, came in and hit it. It knocked out the power, which knocked out the ability of the people running the plant to keep that reaction under control. And so when that happened, they had meltdowns, and it was actually at Fukushima, there were multiple reactors, and a couple of them actually exploded and released contamination to the environment. There's a video for that too if you want to see some more details about just what went wrong with that reactor and the earthquake and tsunami. But the reaction, or what kind of ends up happening after this, is that radioactive material gets spread all over this part of Japan. And what dictates the pattern has to do with which way the wind was blowing at the time of the explosions, as well as where it was raining. So for instance, you can see the wind was going this way, and this red area is the heavily contaminated area. But it also hit these areas here where it was raining, and some of the radioactive particles, particularly cesium, was rained out and then landed into the landscape. And one thing to realize is that these cities around in this area are large cities of 300, 400, 500,000 people throughout here. So you've got about 1 million people kind of living in this area. And all the Japanese government did was really evacuate the areas right over here because they didn't want to have to, honestly, to make a long story short, they didn't want to have to pay to move all the people in these major cities. And so those major cities are still there and still contaminated. But they did evacuate some of these areas here closest to the plant and where the major fallout occurred. One of the things about this, however, is that when the accident was happening, the government basically had warning areas based on these concentric circles away from the plant, but that's not the way the radiation was going. And so there was actually some very sad stories of people that were fairly close to the plant here on the coast who were told to evacuate, and they evacuated into areas over here that ended up getting much more radiation than if they had just stayed where they were because of the way the wind patterns were going. And so, nuclear contamination and issues is one of my particular research interests. I've actually gone to Fukushima and done research in the exclusion zones with other members of the team, and this is us being harassed by the police who are like, what the hell are you doing here? But it was really interesting research to go in and also talk to people that were in these areas where they wanted to evacuate, but were told they wouldn't be given compensation if they did. And this is an area roughly the size of Connecticut that has been contaminated, and large numbers of people still have to kind of live in that environment. And they are trying to do some efforts to decontaminate, but basically what this usually means is just taking all the soil, putting it into bags, and then not really knowing what to do with it. Like for instance, this is a picture I took in Fukushima where they're digging up a lot of the contaminated soil, putting it in bags, and then if you just turn and look across the street, you can just see here's where all those bags are going. They're just setting them over there. And so it's just not necessarily, what do you do with a whole area the size of Connecticut that's contaminated? Where are you going to put that much soil because nobody else wants it? And so they end up just kind of trying to make some areas habitable and then leave the whole surrounding countryside, which of course is still very contaminated. They don't really do anything about it. And then later, a lot of that contamination because of wind and rain and other things will just kind of work its way back down into those valleys. And some of the things that happen then in Fukushima around this is that when people are trying to figure out how to live in these environments, it can be very complex as to where all the radiation tends to concentrate. And so it tends to concentrate in places where water kind of flows, like into ponds, near gutters, next to houses, in certain plants, and mushrooms in particular kind of really soak up the radiation. And so it's created a lot of anxiety and concern in Fukushima in terms of what areas are safe and what are not. And then TEPCO is the name of the company that owns the Fukushima power plant, and they have spent trillions of yen, which is billions of dollars, to try and do some decontamination to compensate the people that had to be moved from their homes. But there's all sorts of issues about who gets compensation and who doesn't, and the company tries to basically pay as little as possible. And there was even a lawsuit where a golf course was saying it had to close because it had so much contamination, and the company that owned the power plant tried to argue and say that once the radioactive particles land on somebody else's property, they belong to that property owner. So they'd say, well, we're no longer, the power company is no longer responsible. If you have cesium all over your property, that's now your cesium to deal with. And that's become a big kind of legal issue there. despite that, people there do try to do it themselves. Some people will do their own soil sampling, where they try to figure out what areas of the prefecture are safe and what aren't. Like I said, the kind of the very small scale or local scale geographies of exactly what areas are safe and unsafe can be very complex, and so people try to get a feel for that. And some people do their own decontamination work, where they try to scoop up their own soil and bury it deep in the ground and get soil that was deeper, that's not contaminated, and put it on top. But this is expensive, earth moving kind of work. And people there are also very active in terms of trying to petition the government and the power company to try and get more compensation. But one thing to remember is that this is an area that wasn't just hit by nuclear contamination. Tsunamis came through here, and there was a devastating earthquake, and so being able to kind of get this area back to what it was before is difficult, and of course the fact that there's nuclear contamination that will be there for decades makes it all the more difficult to kind of deal with or move on from. Right. And the other problem too is that the nuclear the nuclear reactors, they haven't taken all the fuel out. The fuel is still there. It's still burning. And so what's going on is that the groundwater from the nearby mountains is going underneath the plant, going into where the nuclear piles, basically they broke the containment of the vessels they were in and are down in the basements of the building, and groundwater seeping into them, going around these reacting piles of uranium, and then moving out into the ocean. And so what they started doing was just taking that contaminated water and trying to pump it out and put it into tanks. But then all they could do was just put all these tanks of water everywhere. They were leaking, and then eventually they realized they didn't have anywhere to put them, so they let most of that water out into the Pacific anyway. And so this is still an issue at the plant, where it's still, there's still a reacting pile, a nuclear pile in there, and it's still releasing radiation into the environment. Okay, so now moving on to nuclear weapons and how bombs work. So older nuclear bombs, this is an example from atomic bombs, which are the ones that the US first developed in the 1940s and used on Hiroshima and Nagasaki. And a nuclear bomb is actually a fairly simple thing to make. What you are doing in the Hiroshima-style bomb is that you have an explosive that's taking one chunk of uranium-235, and then you have another chunk of uranium-235, and you let off a regular explosive charge to basically just push it together. And when that happens, it gets to a critical mass. You get the chain reaction, and the uranium releases its energy in an explosion. The other way you can do it, and the second bomb that was used on Nagasaki, is an example where it's still basically the same thing, but you have, in that case they used plutonium, but essentially it worked the same as uranium, where you just have it kind of around, and then you have a ball of it in the middle, and then you just explode it to pack it all together into one pile, and then it reacts. Again, the problem with making nuclear weapons, or the difficulty with making nuclear weapons, is not designing them. The problem is getting enough of the fissionable material, in this case uranium-235 or plutonium. Now a hydrogen bomb is a little more complex, but still it essentially, a hydrogen bomb has a atomic bomb in it as its trigger. So the top of a hydrogen bomb works the same way as an atomic bomb, in that you are taking uranium or plutonium and taking one piece and launching it into another piece, which creates an atomic explosion. The difference is that you have some other material here called deuterium or tritium, which is essentially what's sometimes also referred to as heavy water. It's water where the hydrogen atoms have extra neutrons on them. And when you put an atomic reaction next to this, it creates another kind of reaction. It's a fusion reaction that results in an even larger explosion than the atom bomb. And again, if you look back at that fission-fusion explosion, or difference between fission and fusion, that kind of gives you a better example of how that works. But you do need a kind of an atomic trigger to blow up a hydrogen bomb. So there have been about a little over 2,000 nuclear weapons tests around the world, and you can see where most of these have been. Nevada is by far the place that has hosted the most nuclear weapons tests, but you also get quite a few that the US did, and some of the bigger ones out in the Pacific. The Russians did some of theirs in Russia, or the Soviets, but they also did a lot in Kazakhstan. And then you can see other nuclear powers like India and Pakistan have let off their own. China has let off about 41. And then the French have done things in Algeria and then later out here in the South Pacific. You can see there's some places where people probably don't even know that atomic tests were conducted, like Mississippi, Colorado, several up in Alaska, those kinds of places too. Now, in terms of where all the nuclear weapons are these days, Russia and the United States each have roughly 7,000 nuclear weapons. However, they don't have that many kind of active, on alert, ready to go. It's a few thousand less than that for both of them. But in terms of what we could put together on short notice, both countries have quite still thousands of these. This is lower than it used to be. Both the Soviet Union and the United States back in like the 80s had closer to like 10,000 apiece. But they've reduced those stockpiles. And you can see that other countries like France, China, UK, Pakistan, India, Israel all have on the order of like 100 or so nuclear weapons. And of course, North Korea is not on this list, but they now have some, but I think by most estimates it's still less than 10. One thing is one of the videos that you're looking at for this section is about the yield of nuclear bombs these days. The Hiroshima and Nagasaki bombs were very small compared to the kinds of yields that were developed after that and even the yields that we still have today. Those yields were on the order of about 20 kilotons, which means 20,000 tons of TNT. Most of the bombs in the nuclear arsenals today are more like 1 million tons of TNT as opposed to 20,000. So a lot of the nuclear weapons that people have today that are hydrogen bombs are much more powerful than what was used in Hiroshima and Nagasaki. Now, one thing I wanted to mention was, the video command and control that you watch for this section gets into this a little bit, but there have been a lot of very close near misses, times when we almost, either the US or the Soviet Union or others, almost launched nuclear weapons. For instance, in 1960, the US radar installation thought Russia had launched all its missiles, but it was actually the moon that was rising. In 1962, U.S. radars misidentified a satellite as a Russian missile, and they thought that Tampa, Florida, had been nuked. And they only found out it wasn't true because they reacted too slowly to retaliate and launch missiles at Russia. One of the closest ones was during the Cuban Missile Crisis, and this is a little long, but basically there were these Navy destroyers, and they had cornered a Soviet submarine near Cuba. And what they didn't know is that the submarine was in some distress and on the verge of carbon dioxide poisoning. And the crew had no contact with Moscow for days, so they didn't know what had been going on. And the Americans started dropping depth charges to try and destroy the submarine. And it says what the Americans also didn't know was that the B-59 crew, which is of the submarine, had a nuclear torpedo, and that they were authorized to launch it without clearing from Moscow. And the captain of the vessel actually decided he was going to launch this nuclear torpedo at the American ships, which would, of course, launch, the Americans would have retaliated, then the Russians retaliated, and would have been bigger than just one nuclear bomb. And so the captain said he was going to launch it. The torpedo officer said, "We will die, but we will sink them all. We will not disgrace our Navy." So he wanted to launch too. But fortunately, there needed to be 3 officers on board that agreed to launch the nuclear torpedo, and one of those 3 said no. And so because of that, we averted a nuclear exchange. In 1983, there was a guy named Petrov who was a Russian radar person, and the Russian early warning system indicated that the U.S. had launched this large missile attack and that Russia should retaliate. And even though he didn't have any evidence that it was a malfunction, he just, on moral grounds, refused to launch a counterstrike on the U.S. And then, of course, after the fact, turned out that there was no U.S. strike. But that was a case where just one person basically decided not to launch nuclear weapons. Later that same year, this is only like a few weeks later, the Soviets mistook communications from a NATO war game and thought that there was a missile launch at Russia, and they got all their missiles ready to retaliate and launch, but then didn't fire. And then there was a rocket that was launched from Norway, and the Russians thought it was a U.S. submarine-launched nuclear weapon, and Russia went on high alert, gave their president the nuclear suitcase, which is this thing where he can use it to launch a retaliation strike. and ended up that they didn't then launch that strike. So this does happen from time to time where there's been near misses in terms of accidents where nuclear weapons were almost launched. Now, if we look around the world today in terms of potential, conflict areas where we could get a nuclear exchange, of course, stuff around North Korea is always, one possibility. India and Pakistan both have nuclear weapons and are at each other quite a bit. There could also be a potential for a confrontation between nuclear armed powers in around like Russian expansion in the Baltic countries or the Ukraine. Now that many countries have what are called tactical nuclear weapons, which are smaller nuclear weapons, there's the concern that people might use, or armed forces might use one of those smaller nuclear weapons, and then that would force the other country to use one too, and that could escalate to larger and larger nuclear strikes. Of course, Iran may get nuclear technology, and then what might happen between a nuclear-armed Iran and nuclear-armed Israel or US, and that sort of stuff comes into play. And of course, there are also potentials of terrorists getting hold of nuclear weapons and using those. And other potential flashpoint would be a potential conflict between US and China, potentially in something like the South China Sea or East China Sea, where both of these militaries are sort of claiming the ability to use those spaces. Like the US says this is international waters, and the Chinese are trying to say, no, it's Chinese waters, and there's a lot of potential conflicts that could arise there between the US and China, which, of course, both nuclear-armed powers. And this is just that area, the South China Sea and the East China Sea here, that are kind of potential flashpoints. Particularly a lot of the islands out here, which China claims all of them all the way down to here, and other countries claim different sections, and the US says that this should also be international waters that people can go through, so that's kind of created tension between some nuclear-armed powers. All right, so you've got some of the other videos here that make sure you should watch. And that's it for this module. All right. Hope you enjoyed our brief tour of potential nuclear death. Thanks.